Hello, everyone, and welcome to Lowell Observatory's Meet an Astronomer. Today we have a special guest, a mentor of mine, Dr. Tyler Robinson from Northern Arizona University. He's an expert in exoplanetary science, exoplanetary atmospheres, and astrobiology. Let me know if I miss anything, Ty. But before we get into Q&A with him, I'm going to turn it over so that he can tell us a little bit about what he does. Ty?
Great. Thank you, Megan. So I want to take some time to tell everyone about exoplanets, which are planets that are orbiting other stars. And so, figuring out how to advance slides here. To begin, I'm going to take us all back to the far off and distant time of 1995. The mindset of astronomers at the time was that we thought we understood our solar system quite well, and we also thought that other planetary systems around other stars were going to be very similar to our own. So what I'm showing you here is obviously a solar system that isn't our solar system, which isn't to scale, but we have Mercury, Venus, Earth, and Mars in the inner parts of the planetary system, the rocky planets of our solar system. And then in the outer parts of our solar system, we have the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune. We astronomers were very much under the impression that when we looked out to other planetary systems, what we were going to see was the rocky planets on the inside of the system and the gas giant planets on the outside of the system. The reason why we were so confident in our understanding of how planetary systems should appear and why they should appear like our own planetary system comes from our ideas of how stars form. And so stars form out of a vast collection of gas and dust in the medium between stars called the interstellar medium. That gas and dust collapses on itself. A star is born at the center of that collapsing cloud. A disk of material forms around the outskirts of that forming star. And then inside of that disk is where you're able to form planets. And the portions of that disk that are closer to the star should be warmer than the portions of the disk that are far from the star. And so the portions of the disk that are far from the star should have things like water ice and carbon dioxide ice present in them because they're so cold, whereas those materials are going to be evaporated in the warmer parts of the disk. And so the presence of all of that ice beyond what is called the frost line provides the essential materials that you need to build up enough mass to form a gas giant like Jupiter, Saturn, or an ice giant like Uranus and Neptune. And so because that frost line is located far from the star, we were under the impression that giant planets should always be forming and should reside far from stars, whereas rocky planets, which don't form from much or any icy materials, just from rocky materials, should reside close to the host star. So around the same time that our understanding of planet formation was coming around, and we were so confident in our understanding of planet and planetary system formation, another group of astronomers was being pretty clever about techniques to search for planets around other stars. And what these astronomers remembered or realized is that planets don't just go on an orbit around a stationary star at the center of their orbit. Both the star and the planet actually orbit their common center of mass. And so that is actually what this nice little video shows here, is a cartoon of a planet and the star doing an orbit about their center of mass. And the center of mass is essentially, if you were to connect that star and that planet with a rod, where you would need to put your finger such that that rod would be balanced on your finger. It tends to be located much closer to the star than to the planet because the star is much more massive than the planet. And really, this is just a consequence of what Newton told us, which is for every action, there's an equal and opposite reaction. And so while that star is tugging on the planet, causing it to do an orbit, similarly, the planet is tugging on the star, causing it to do its own tiny little orbit. Here's a nice cartoon of the dance that our own star, the sun, has done over the last several decades. You can see that it does this nifty little kind of spirogram dance it's about the solar system's center of mass. But really what you're seeing here is primarily a response to Jupiter, which after the sun is the most massive body in our planetary system. And so the sun is responding to the gravitational tugs of Jupiter and doing a little wobble or a little dance in response to those gravitational tugs. And so what these astronomers in the mid-90s um, put together with the idea of stars that have planets going around them should be doing a little wobble, they also realized that when that star is wobbling towards us here at Earth, that the Doppler effect says that the light from that star should be ever so slightly shifted towards blue wavelengths. And when the star is moving away from us, the light from that star should be ever so slightly shifted towards red wavelengths. Those of us here on Earth don't have much experience with the Doppler effect when it comes to light, but we've all probably encountered it when it comes to sound. When there is an ambulance or a police car coming towards you with the sirens on, you hear it at a higher frequency or higher pitch when it's coming towards you than when it's going away from you. Or if there's a train coming towards you and the train is blaring its horn, it sounds at a higher pitch or higher frequency when it's coming towards you than when it's going away from you. Light does the exact same thing. It's just very difficult or impossible really to detect with our eyes. We need specialized instruments to be able to detect this because for the kinds of speeds that we're talking about here, for stars doing their wobble, it is a very subtle effect. But these astronomers in the mid-90s set about building the kinds of instruments that would be sensitive enough and that we would need to be able to detect planets around other stars. And this led to the very first detection of an exoplanet around a sun-like star. And this planet has a really exciting name of 51 Peg B or 51 Pegasi B. So it orbits the star 51 Pegasi, and then for the first planet found around that star, it gets a lowercase b. The second planet would get a lowercase c, and so on. Admittedly, not a very fun way of naming worlds around other stars. But what was so amazing about this first exoplanet found around a sun-like star is that it had a mass that was comparable to Jupiter in our own system. So it was a gas giant exoplanet, but it was tucked in extremely close to its host star, 10 times closer to its host star than even Mercury is to the sun in our planetary system. And so a consequence of that is that the planet is extremely hot. Temperatures in the atmosphere of this planet reach comparable temperatures to, say, the center of a roaring bonfire here on Earth. It's extremely hot in the atmosphere of this planet. And so we call these kinds of worlds hot Jupiters. And so 51 Pegasi B is really the quintessential hot Jupiter. But you probably remember that just a few minutes ago, I was telling you that, again, in the mid-90s, we were confident that we were going to find rocky planets in the inner parts of planetary systems and gas giant planets orbiting far from their star. And here, the first exoplanet around a sun-like star that we found completely breaks that idea. It's a giant planet orbiting very close to its host star. And this completely revolutionized our understanding of planet formation and planet evolution in the ensuing years. And so now we know that not only do planets not have to stay in the same location as they're forming, but planets after they form can even move their orbits. And so planets can do a thing called migration. And so migration is a movement of the orbit that can explain how a gas giant planet would form very far from its host star beyond the frost line and could move inwards and wind up like a hot Jupiter, like 51 Pegasi B that was discovered in the mid-90s. These days, it's not just the wobble technique or the Doppler technique that we use to find exoplanets around other stars. There is a new kid on the block that has put up huge numbers for discovering exoplanets. And so this technique relies on what are called planetary transits. And so here is a nice image of a transit that occurred on our own solar system. This is the transit of Venus across the disk of the sun in the early 2000s. It happened again in 2012. If you missed it then, I think you're out of luck because it's going to be about another 100 years before Venus does this amazing thing from our perspective here on Earth. And what you can imagine is if you had a telescope connected to a device to measure the brightness of our sun, and say maybe you put that telescope high enough up on a mountain that you didn't have these pesky clouds in the way, and you were to monitor the brightness of our sun over time before the transit of Venus, during the transit of Venus, and after the transit of Venus, that you would see the sun is relatively constant in brightness up until Venus starts to transit the sun, and then the brightness of the sun would ever so slightly decrease because of the fact that Venus is blocking out a patch of the sun from our perspective, causing a dimming of the sun, and then the sun's brightness would return to normal after the transit of Venus. there's a question here from Jacqueline. Is true flash solar tomorrow? Probably a question about a solar flare tomorrow or something like that. Maybe Jacqueline can.
Oh yeah, I saw something about that like online, that there was supposedly a solar flare. I don't know if you know anything about that, but I haven't.
There was a news story this morning that I heard that was talking about solar flares, and so maybe that was in response to a flare going off. But it does take time for the flare material to make it from the sun to us here on Earth, and so it could very well be that a flare has gone off and that there's some material headed our way, which is exciting for people who get to see the northern lights. Or the southern lights. The challenge, though, for exoplanets is that stars that aren't the sun are so far away from us that we don't actually see the disk of that star. They're just a single point of light from our perspective, and so we can't actually see the planet going across the disk of that star. What we are stuck doing is just monitoring the brightness of that star to see if it periodically gets ever so slightly dimmer because of a planet on a periodic orbit from our perspective crossing across the disk of that star. And so this is called the transit technique for detecting exoplanets. Many of you may be familiar with the transit technique because of a very famous NASA mission, NASA's Kepler mission. It stared at a patch of the night sky in the constellation Cygnus. It looked at about 100,000 stars, and all it did was very carefully monitor the brightness of those stars to look for periodic dimmings that could be caused by planets going around those stars. And the Exoplanet Hall from Kepler has been truly amazing. And so these are the number of exoplanets detected in any given year leading up through 2016. So if you go all the way back to 1995, which is when 51 Pegasi B was discovered. So there was a single planet detected that year, and you can't really see that even on this scale because thanks to the Kepler mission and the successor to the Kepler mission, which was a reuse of the spacecraft and the K2 mission, if you look at the light blue bars here, that is the Hall of exoplanets from Kepler and K2. And then the orange here is also additional discoveries from Kepler and K2. So thousands of exoplanets have been discovered thanks to NASA's Kepler mission and NASA's K2 mission. And there's an ongoing mission right now funded by NASA called the Transiting Exoplanet Survey Satellite, which is using the same technique as Kepler, staring at stars, looking for periodic dimmings, that is detecting exoplanets and reporting those even as I give this presentation. So it's an ongoing NASA mission. And so what exoplanets have really done for us is they have completely expanded kind of what we thought a family portrait of worlds or planets should look like. And so that expansion now includes all kinds of crazy planets and types of worlds that don't exist in our own solar system, but have a lot to tell us about how planets form and how planets evolve. I've already told you about one of these, the hot Jupiter 51 Pegasi B, which completely changed our understanding of how planets move after they form. But there have been a number of notable discoveries in the field of exoplanets. I'm just going to highlight some of my favorite exoplanets that have been discovered. There is a exoplanet discovered by a European satellite called Corot 7b. So this is a world that is known to be rocky. It is a little bit larger than our Earth, and so we call it a super Earth. It doesn't mean it has any special powers or anything like that. But it's not just hot Jupiters that are tucked in very close to their host star. Corot 7b is tucked in even closer to its host star than 51 Pegasi B is. And so dayside temperatures on Corot 7b are so extremely hot that they approach the melting point of rocks. And so it could be that the rocks on the day side of Corot 7b are melted and that there's a magma ocean that forms on the day side of Corot 7b. One of my favorite exoplanets is a world, again, with a very boring name, GJ 1214b. So it orbits the star Gliese 1214, and it's the first exoplanet discovered around that star, so you get the lowercase b. GJ1214b has a size that is intermediate between Earth and Neptune in our planetary system. Neptune is about 4 times larger than our Earth. The density of GJ1214b is fairly light, indicating that it has it's not fully like Neptune, and it's also not fully like Earth. And so it's completely mysterious because we don't have anything in our own planetary system that resides in between the sizes of Earth and Neptune. So this is a very exciting category of planet just because we don't know hardly anything about what these worlds are like. Do they have solid surfaces? What are their atmospheres composed of? And how do these worlds form and evolve are completely open questions for astronomers that we're working on these days. And so, if I didn't say it already, we often refer to these worlds as mini Neptunes or sub-Neptunes. And so I think a question that many people have, and one that I'm excited to be working on and trying to answer, is, well, have we actually discovered anything out there that looks like this? Have we found any other Earths out there? And the shorter answer is that we don't know, because the Doppler technique or the wobble technique is sensitive to the mass of the planet, and the transit technique is sensitive to how big the planet is, the size of the planet. We have discovered planets where we kind of know something about their mass. We know maybe that they're similar in mass to Earth. We've discovered planets where we know something about their size, so we know that they're similar in size to our Earth. And we've also discovered planets that are on orbits that are within the habitable zone of their host star. And so the habitable zone, or the Goldilocks zone, is really just the range of orbital distances where an Earth-like planet could have an ocean on its surface. And so you imagine that if you take something like the Earth and tuck it in too close to its host star, it gets too toasty, and the oceans all want to boil off and evaporate. If you take something like the Earth and move it too far away from its host star, it gets cold. And as a result, the oceans would freeze over. But there is a middle range there where you could expect to have oceans on the surface of the planet, and that's called the habitable zone. And so we have found things that are similar in mass to the Earth, similar in size to the Earth, and in their host star habitable zone, which is, of course, really exciting, but that doesn't yet tell us if they're exactly like the Earth. There was a question here from Jasmine. It says, using the transit method, why is it easier to find planets that are closer to their star? It's a really good question. And so there's really a couple of things at play here. First of all, planets that are on orbits that bring them in closer to their host star are more likely to transit their host star from our perspective. And so the probability that we see a planet transiting goes up as the orbit gets smaller. And so that kind of biases us towards detecting things on close-in orbits. But the other nice thing is that if you're on a close-in orbit, Kepler also told us this, the orbital period is shorter. And so in a given amount of time, you observe many more transits for something that is on a close-in orbit than something that's on a faraway orbit. And so if, say, your space telescope only lives for 4 or 5 years, and you want to see several transits to make sure that the dimming that you're seeing is indeed periodic and due to likely a planet, then there's a limitation that is then set on how those planets need to be close in for you to observe enough transits over the lifetime of your telescope. Question from Charles. Would it require a solar system-sized telescope using sun as a gravitational lens has been suggested to directly image even a nearby planet, Proxima Centauri B, for example? I will get to this a little bit later in the presentation. It is true that people, some really innovative thinking astronomers, have proposed an idea for using how the sun, through principles in general relativity, can bend and focus light, because the sun isn't so massive, that you could build a telescope, send it far out in the solar system where that focusing happens, and potentially image Earth-like planets around other stars. But not only image them, because the focusing of the sun is so great, you might even be able to resolve the surfaces of these planets. And so you could do things like see weather and see continents and see oceans on them. This idea is extremely new. And so the study of this telescope only came out within the last year. And so many of the ideas are still being sorted through by the astronomy community. But independent of that, there's other work going on for being able to directly image planets around other stars, and I'll get to that in just a second. Thanks, Charles, for that question. Now, I'm going to give you a few examples of planets that have been found that are in their host star's habitable zone. So if they were indeed like the Earth, they could have oceans on their surface. And so one of those is the exoplanet Proxima Centauri B, here shown with a artist's representation. What we know about Proxima Centauri B is discovered with the wobble technique. So we know that its mass is at least a little bit larger than Earth. And we also know that it kind of lies smack dab in the middle of the habitable zone of its host star. So indeed, it could have oceans on its surface, but that's all we know yet about Proxima Centauri B. What's so exciting about Proxima Centauri B is that if you think about kind of the solar neighborhood and put up a map of all of our stellar neighbors in the solar neighborhood, the nearest stars to the sun is actually a triple star system. So it's Alpha Centauri A and B, which are naked eye stars that you can see in the southern hemisphere. And then on a much wider orbit around Alpha Centauri A and B is a faint M dwarf star called Proxima Centauri that you can't see with the naked eye, but that has this famous exoplanet Proxima Centauri B orbiting it. And so that means that the nearest planet, or the nearest stellar system to our own sun, has a potentially habitable exoplanet residing in it, which I think is very exciting. There was another question, which was from Gary. If we are looking for an Earth-like planet, would they not be more likely to be found around class K stars than class M stars, with class K having more stable flux? And so Gary here is talking about different types of stars. And so stars come in a variety of temperatures. And so there are very hot stars called O and B type stars. There are intermediate temperature stars like the sun, which is a G-type star. And then there are stars cooler than the sun, which are K dwarfs and M dwarfs. And so Gary's talking about the coolest types of stars, K dwarfs and M dwarfs. And so Gary's wondering if maybe planets like our Earth might be more likely to be found around K dwarfs than M dwarfs. And so the short answer here to Gary's question is we don't know. M dwarfs, the smallest, faintest types of stars, present a number of challenges to having habitable planets orbiting around them. M dwarfs have an extended active phase where they do lots of flaring, and that could be detrimental to, say, life, or could also have impacts for, say, oceans on these planets. M dwarfs also, as they're forming, take a really long time in some cases to settle down and become a stable star. And so they have this thing called a pre-main sequence lifetime that is long, where the star is actually brighter than it usually is once it is a regular old main sequence star. And so that means that a planet that is in the habitable zone today, once a long time ago, was being cooked by this pre-main sequence M dwarf star, which could have boiled off the oceans. And so there are a lot of challenges to forming and maintaining habitable worlds around M dwarfs. And so what I think is exciting about missions that are coming up that NASA is going to launch that have the ability to characterize atmospheres of potentially Earth-like planets around M dwarfs is it can kind of test the question here that Gary put forth, which is, can you have Earth-like planets around M dwarfs? We don't know the answer to it yet, but NASA is building the telescopes and will launch the telescopes that have the capability to answer that question. Another extremely famous now exoplanet system is a planetary system that was discovered using the transit technique around a relatively nearby, extremely faint, extremely cool M dwarf star called Trappist 1 is the name of the star. And it has a planetary system that has at least 1, 2, 3, 4, 5, 6, 7 different planets in it, all with the letters shown here in the order of discovery. But 3 or 4 of these planets reside comfortably within the habitable zone of Trappist 1. And so in this single planetary system, there is not only one, but there's a handful of potentially habitable, potentially Earth-like planets in these systems, in this system. And what we do know about the Trappist systems, there's my dogs, is that because they're found with the transit technique, we know that their size are all pretty comparable to Earth. Because their host star, TRAPPIST-1, is so small and so faint, for these worlds to be habitable, they have to be tucked in really close to their host star. And so what this graphic does a really nice job of showing is that this entire planetary system of all of the TRAPPIST planets is tucked in extremely close to its small, faint host star and would all reside within the orbit of Mercury if they were to be transported to our own planetary system. And just to put it in perspective, here's a nice artist rendition of the size of TRAPPIST-1, again, one of these faint, cool M-dwarf stars compared to our own sun. And so TRAPPIST-1 is about 1/10 the size of our own sun, which actually is what was critical and played a key role in helping to be able to find the relatively small planets around TRAPPIST-1. And so as I've kind of alluded to, for all of these planets, we either know something about their size, we know something about their mass, maybe we know both the size and the mass, but that's really all we know about these potentially Earth-like planets around stars. And our own solar system gives us kind of a warning message for interpreting worlds just based on their size and their mass. So our sister planet in our planetary system, Venus, has roughly the same mass as our Earth, has roughly the same size as our Earth, but has a surface that is a hellish landscape. So the temperatures at the surface of Venus are about 900 degrees Fahrenheit, and that's hotter than your oven set to self-clean, so not a habitable environment, but the same size and the same mass as our Earth. And so if you really want to know if something is truly Earth-like, you'd like to know the size, you'd like to know the mass, but you'd also really like to know something about the atmosphere. And this is a research area that my own group here at Northern Arizona University specializes in. And so now when you look at Venus and Earth, you can see two very different worlds. You can see that Venus has a carbon dioxide-rich, CO2-rich atmosphere that's almost 100 times thicker than our Earth's atmosphere, whereas the Earth's atmosphere shown here is a little bit more than 75% nitrogen and and a little bit under 25% or a quarter oxygen, which is due to life on our planet. And so it's the difference in atmospheric compositions for these worlds that tells you that these are, that one is a habitable planet and one is not a habitable planet. So what is very exciting is, at least as currently stated, in under a year, NASA is going to be launching the James Webb Space Telescope, which is going to be a very large telescope sent away from Earth, sent to space. And James Webb may have the capability to study the atmospheres of rocky exoplanets orbiting cool these M-dwarf stars. And so, for example, the TRAPPIST-1 planetary system, the potentially habitable worlds in that system, the potentially Earth-like worlds in that system, are going to be prime targets for the James Webb Space Telescope. And so James Webb may give us an opportunity to know whether or not these worlds are actually Earth-like, whether or not they have the potential to have oceans on their surface, and whether or not there are any signs of life from these planets, say oxygen in their atmosphere as is a sign of life for our own planet. NASA, of course, is an agency that thinks beyond the scope of just the next mission that it's going to launch. And so NASA has studied a number of different space telescopes that could follow after James Webb Space Telescope that would have the capabilities to study Earth-like planets around nearby stars that are like our sun, not necessarily cool M-dwarf stars like is going to be the specialty of James Webb. And so these are going to rely on a technique that is called direct imaging. One of the questions from a viewer earlier on was talking about imaging stars around imaging planets around other stars. This is something that we can do currently, as shown here. And so this is a exoplanetary system that has 4 gas giant planets in it, orbiting a star. That star is very young, and so those planets have only recently formed, and so they're still quite hot, which makes them easier to spot. But the same technology, which is called direct imaging or high contrast imaging, could be employed on a future space telescope. And we might be able to take images like this of planetary systems around nearby stars revealing things like Venuses in those systems, Earths in those systems, and Jupiters in those systems. And this is just a simulation of what those kinds of missions might be able to do. And so with these missions, you would be able to take the light from that potentially Earth-like planet and disperse it, so break it up into its constituent colors, such that you have a spectrum. And so here's a spectrum of our planet shown as kind of the relative brightness of the planet at different wavelengths, which is what the astronomers use. You can think about those as being colors. And so as I have highlighted right here, at colors that are a little bit redder than what you and I can see with our eye, there is a feature due to oxygen in our atmosphere where oxygen does a good job of absorbing light, and so it creates what's called an absorption feature. And so that feature in the spectrum of our own planet is indicative that our planet is inhabited and has oxygenic photosynthesis going on it. And so it'd be really exciting with these future missions to be able to take a spectrum of another world and potentially see oxygen in the atmosphere of that world, which could tell us that there's life present on that planet. And so with that, I have wrapped up my slides, and so I'm happy to take more questions. I really appreciate the questions that have come in so far, but I'm happy to hear more questions from the viewers.
Awesome. Thank you so much, Tyler. Yeah, if anybody has any questions, please put them in the comments section, and our friends at Lowell make sure that we see them. While we're waiting for people to answer some questions, I have one for you. Could you say beyond a reasonable doubt that a planet is habitable without visiting it?
I think yes. And so for an exoplanet to be habitable, what you would like to know is whether or not there are oceans on its surface would be a telltale sign of habitability. And so there are a number of ways to tell if there is an ocean on the surface of the exoplanet. And so one of the listeners already talked about having some kind of futuristic telescope that would actually enable you to take a picture of that planet that resolves the surface. And if you saw continents and oceans on it, that would tell you that that world is habitable. But there are other ways of going after detecting habitability or detecting oceans on exoplanets. The one that my research group has put the most amount of effort into studying is to look for a feature called glint from an exoplanet. And so anyone who is watching this and who has ever seen a picture of or watched a sunset on a beach here on Earth, you know that when the sun is getting really low in the sky, you get all this beautiful reflective orange light that comes off of the ocean, and that's what makes sunsets so nice to watch off of beaches. What you're seeing there is glint. And so it turns out that when light comes in at a very shallow angle and reflects off of water, the oceans become very reflective. And so this dramatic increase in the reflectivity of oceans is something that you might even be able to spot for Earth-like exoplanets with a future NASA mission by observing that planet when it becomes kind of a faint crescent sliver where you're observing light coming in at very shallow angles and reflecting off of the surface.
Thank you. Can you go back to your title slide real quick? And also, we have a really good question from Charles. This question is actually really near and dear to my heart. What are the real capabilities of the James Webb Space Telescope for determining exoplanet information?
So this is an active area of research right now. Megan, as she just mentioned, is doing research in this area. And the short answer is we won't know what James Webb's capabilities are for studying exoplanet atmospheres until it launches, and then we'll have a good understanding of how it's functioning and what its true capabilities are. It is anticipated that James Webb is going to do an exquisite job of getting us atmospheric information for things like hot Jupiters and hot Saturn and hot Neptune-sized worlds. But for worlds that are smaller than that, and so things that might be rocky exoplanets or definitely rocky exoplanets, it is not yet known how well James Webb is going to be able to characterize those atmospheres. And so the atmospheres of potentially Earth-like exoplanets are kind of right on the cusp of what James Webb might be able to do. And so I think that makes it all the more exciting to then try to do this with James Webb. And of course, it's already been proposed, and the exoplanet community is behind spending some James Webb's observing time, trying to go after the atmospheric constituents of the world in the Trappist exoplanet system, TRAPPIST-1 exoplanet system.
Thank you. So the next question comes from Terry. In the 70s, NASA Ames research was doing studies on the potential of life existing in atmospheres consisting of other than oxygen and nitrogen. Was there any success there? So I think, in other words, maybe is there a possibility for not carbon-based life?
Yes. And in fact, research in that area has continued. Just within the last month, there was a publication from a colleague and mentor of mine, Professor Sarah Seeger, who is at the Massachusetts Institute of Technology, who was able to grow some microbial life in a pure hydrogen, H2 environment. And those organisms were able to do just fine. And so not only does that, so that shows that Earth-like life can exist in different kinds of environments, but also astronomers and astrobiologists are busy thinking about other kinds of atmospheres that could have other kinds of life that aren't like Earth. And so the concept of the habitable zone and the listing of biosignatures and going after molecular oxygen as a sign of life are all very Earth-centric. And I think that's a good place to start when it comes to searching for life on exoplanets. It's like, start with what you know. But I think some of these missions that I've been alluding to, or maybe even future NASA missions, would have exciting capabilities to hunt for signs of life from biospheres or kinds of organisms that aren't anything like life on our planet. And so I'm excited about the prospect of weird life on a variety of other kinds of worlds.
Thank you. So our next question comes from Chuck. He said he missed the first few minutes, but is there any way to detect an exoplanet with an orbital plane perpendicular to our line of sight? So if the planet doesn't transit.
There are a couple of techniques that would enable you to do this. And so the one that is under most study right now and might actually yield some exoplanet detections in the near future, thanks to a European mission called Gaia, uses a technique called astrometry. And so here, what you actually do is you monitor the position of a star in an image, and what you would try to see if you can actually witness the star moving around in the image and doing a tiny little circle in the image. It's extremely difficult to detect. And the Gaia mission is really a feat of engineering and science, in that they're able to do this. But then if you have a star in the middle and you have a planet whose plane is perpendicular to our line of sight, then you would, for the astrometric technique, you would get the strongest astrometric signature of that star doing a full circle in response to that planet going around it. And so the astrometric technique could be able to do this, and it's predicted that the Gaia mission should get detections of this. And then the direct imaging technique that I talked about towards the end would also be able to find exoplanets kind of independent of however their orbits are oriented from our perspective. And so it can find orbits that are perpendicular to our line of sight and orbits that are parallel to our line of sight.
Awesome. Thank you so much. So our next question comes from Jasmine. Objects that are Doppler shifted are shifted from what exactly? How do astronomers know what the object's original spectrum looks like? It's a good question.
Yep. So there are a few techniques for measuring this slight blue shift and this slight red shift. And so usually what is done, though, is you take a cell of that has some kind of gas inside of it, like iodine gas or sodium gas, and that gas has its own set of absorption features that occur at very specific wavelengths. And what you can do is you can pass the light from the star that you're observing through that tube of gas, and what that then happens is that star's spectrum then gets imprinted on it, essentially a barcode of a bunch of lines that are the absorption features for that gas that's in that cell. And so now you have this grid of features, this barcode that you can then see, quote unquote, the star's spectrum moving back and forth relative to those features that you have then imprinted on top of the star spectrum, is an early technique that was used, and a very fruitful technique that has been used. But yes, the blue shift and the red shift is very subtle, and so it requires careful engineering and careful thought to be able to measure the shift towards the blue or the shift towards the red relative to something.
Awesome. Thank you so much. So our next question is a little bit like the one you answered about life growing in atmospheres that aren't oxygen and nitrogen based. So this comes from Ultimate Misfortune. Since we see hydrocarbon lakes on Titan, do you think it would be possible to see different forms of life not based on oxygen on these exoplanets? So perhaps you could speak a little to Titan and our potentially habitable moons in our atmosphere, or in our solar system.
Yep, so Titan is a moon of Saturn, and as the listener points out, it's known that Titan has a liquid on its surface. It's not liquid water, though. It's liquid methane and liquid ethane forming lakes on the surface of Titan. And so astronomers and astrobiologists and scientists have proposed that you could form weird kinds of life who use a solvent that isn't water, like that life uses here on Earth, but is liquid methane or liquid ethane, and have that kind of life be happy on the surface of Titan. That life hasn't been detected yet. It's just been proposed. And so Titan is not the only moon in the solar system that people are excited about and think that there could be life present on. Many listeners have probably heard about the moon Europa, which is an icy satellite that orbits Jupiter, and it's known that Europa has a liquid ocean underneath its icy crust. And that ocean, the volume of that ocean is actually larger than the volume of our own Earth's ocean. So it has a large ocean. It has a rocky interior, and it's very likely that there's energy coming out of the interior and into that ocean. And so it could be that there are life forms that exist on Europa that take advantage of that energy. When it comes to hunting for weird life on exoplanets, the short answer here is that if that life produced a signature that was blindingly obvious, even though that life is weird, these future telescopes would be able to detect it. Where we get into trouble is that because astrobiologists are pretty narrow-minded right now in our understanding of the kinds of features that life can produce, we have a really good understanding of what Earth-like life can produce as far as biosignatures, but a not so good understanding of what weird kinds of life might produce as biosignatures. And so it might be that we observe an exoplanet with a future NASA mission, and that we see a strange concoction of gases in the atmosphere of that exoplanet that aren't indicative of any kind of life on Earth, but also we cannot prove beyond a reasonable doubt are due to some weird kind of life, because we don't have a great understanding of that weird kind of life. And so we may end up in a situation where we have exoplanets that have weird atmospheric signatures that we can't fully explain, but we also can't fully argue that those come from life.
Thank you. So you mentioned biosignatures. Would you be able to briefly define that for everybody here?
Yep. And so most broadly, a biosignature is just a sign of life. And so for people who work in exoplanets, we usually think about studying the chemical composition of an exoplanet atmosphere to hunt for signs of life. And so in our own atmosphere, there are a number of gases that are biogenic, so they are created by life. Oxygen is a biogenic gas and is thus also a biosignature gas. Methane is created by life here on Earth. It's also created by abiological processes, so processes that don't involve life. And so it can be an ambiguous biosignature. And there are a number of other gases that also are created by life here on Earth that we think, if we were to see in the atmosphere of an exoplanet, would be at least a possible sign of life on that exoplanet. Life also does other things that are biosignatures. And so, for example, trees here on our planet have pigments, and that's what makes them green. And so it could be that you might be able to detect pigments on exoplanets due to life on its surface. if your eyes could see a little bit further into the red, plants would actually seem much more reflective to you than they actually appear with our usual eyeballs. And so there's this thing called the vegetation red edge, which is at redder wavelengths, plants become suddenly reflective. And so in the spectrum of Earth, you can actually see this vegetation red edge. So it's another kind of biosignature. And then there's a whole category of biosignatures, which are called technosignatures. And so these would be signs of life that come from intelligent organisms. And so, for example, radio signatures or something like that coming from an exoplanet would be a sign of life there, and would be a technosignature. So there was something on that planet that had the capability to build, say, a radio telescope or a radio transmitter that is alive.
Thank you. So next question comes from Gary. What instruments, if any, at Lowell Observatory are used in exoplanet research? Discovery telescope of particular interest.
Yes. So I don't have a full rundown of all of the telescope capabilities up at Lowell Observatory, but for the Discovery telescope, there is an instrument at the Discovery telescope called Express. And so, and as I guess we should be pointing out here, that so it's the Lowell Discovery Telescope, is its new name that we're all using. And so there's an instrument called Express on the Lowell Discovery Telescope, and it is a hypersensitive instrument for doing radial velocity or Doppler or wobble observations of stars. And so the goal of Express is to push the limits of the kinds of exoplanets that can be discovered down towards very low mass, say Earth mass exoplanets. And so Express has only recently come online at the Lowell Discovery Telescope, but is a instrument that's at the forefront of being able to detect small exoplanets using the Doppler or the wobble technique when looking at spectra of stars.
Thank you. I'm just going to add to that quickly. The Lowell Discovery Telescope isn't just our only discovery telescope at Lowell Observatory. We also work with the Naval Precision Optical Interferometer, or NPOI. So this is a collaboration with the Navy. And NPOI uses a really exciting form of observation called optical interferometry, which is a really fancy way of saying that we use multiple telescopes that work together to take one observation. So really, you can use all of our research sites to do all sorts of projects, not just in exoplanetary science. Now moving on to Terry's question. Could an exoplanet exist in the habitable zone of a binary system, and what would that orbit look like in relation to the two stars?
So the short answer is yes, you can have a habitable planet in a binary star system. And so by and large, there are two different ways you can put that orbit together for the binary star system. And so what you could do is you could have two stars, a binary star system where the stars orbit very close to one another, and then you have a planet that is in the habitable zone of those two stars orbiting around the pair of them. And so that's one way that you can concoct a habitable planetary system around a binary star system. The other thing that you can have is you can have a central star that has a planet orbiting around it, and then a secondary star that is the binary star on a much wider orbit around the two. And so there are ways to also make that system habitable. So if the binary star is very far away from the central star, then the sunlight from that very distant star doesn't impact the habitability or the climate of the planet in here very much. Or it could be that if this more distant binary star is relatively close, that this planet in here happens to orbit at the right distance where the combined light from the central star and the star in a distant orbit, when put together, give it enough energy to have oceans on its surface and not be too warm and not be too cool. And so there have been exoplanet discoveries in binary star systems. And so it's not just science fiction anymore. We do know that planets exist in binary star systems. And it'd be probably just a matter of time before we start detecting and trying to understand habitable planets in binary star systems.
Thank you. So our next question comes from Charles, and I think we briefly touched on it with oceans and technosignatures, but what would it take for unequivocal evidence of exoplanet life?
I think this is a very challenging question to answer because I think scientists are going to have their own. Each individual scientist is going to have their own threshold for what they think is unequivocal evidence for life. And I also think non-scientists who are interested in this are going to have their own thresholds for what they think is an unequivocal sign of life. And there isn't really a right or wrong answer there. So I like to think if we built a space telescope and we imaged planets around a nearby star that's very similar to the sun, and we saw a planet in the habitable zone whose size and mass was similar to that of our Earth and whose atmospheric composition was extremely similar to that of Earth, and that it had oxygen in its atmosphere, had ozone, had methane. I think that would be an unequivocal sign of life if you spotted a true Earth twin. But I don't think the universe is going to be that kind to us. I think that the kinds of planets that we're going to detect and try to study are going to have a huge range of atmospheric compositions, and it's going to be very difficult to state unequivocally whether or not there is life present on that planet. The caveat, though, I think comes from the search for extraterrestrial intelligence, or SETI, and their search for, and the associated search for technosignatures. I think a technosignature is going to be a very unequivocal sign of life. If you get radio signature or some other kind of signature from intelligent life on a planet, then you're going to be confident in knowing that there's something living there, or there was something living there that built robots or something like that, which is still a sign of life that isn't our own.
Thank you. So our next question also comes from Charles. In those systems for which you have imaged gas giants, how easy would it be to detect any exomoons? So I'm just going to expand that to not just the imaged gas giants, just detecting moons in general.
So for the current crop of directly imaged exoplanets, the technology just isn't quite there yet to be able to spot moons around those planets. The moons are even fainter than the planets that they're orbiting around, and so the technology just isn't able to detect these very faint moons. Plus, the moons orbit very close from our perspective to their host planet, and so the light from those moons, even if we could detect it, would probably be blended with the light from its very bright host planet that it's orbiting around. There have been a number of techniques proposed, though, for trying to detect exomoons. And there have been some claimed discoveries of exomoons to date that I think are debated in the literature. So again, not unequivocal detections of exomoons. And so for, say, the transit technique that we've talked about, if a transiting exoplanet has a relatively large exomoon orbiting around it, you might see that in the dimming of the light of the host star. The exomoon orbiting that planet also tugs gravitationally on that planet. And so by monitoring the timing, so you sit there with your stopwatch and you watch the orbit of that planet going around its host star, if the timing of those dimmings changes in a way that is indicative of a moon tugging on that planet, you could also detect a moon that way. And there have been some suggestions of ways to use direct imaging to detect exomoons, even if you can't separate out the bright planet from the faint moon orbiting around it. There are still ways where light from that moon gets blended with the light from the planet in ways that indicate that there is a moon present. And so I think in the very near future, we're probably going to have unequivocal detections of exomoons. And there are a variety of techniques that now exist that people have proposed and discussed and are working on to try to detect these exomoons.
Thank you. So we have no more questions coming from the public, but I actually have one for you before we wrap up. And that is, how can the public get involved in exoplanetary science as amateur astronomers?
So I think there are probably many ways that people can get involved in exoplanetary science. There are amateur astronomy efforts put together to do transit observations, and some amateur astronomers have actually been on scientific publications where exoplanets have been discovered. There are online efforts that are kind of like Galaxy Zoo, but for exoplanets, where the public can pore over data from missions like the Kepler Space Telescope and try to spot transits in the data that maybe the computers missed. And the general public has actually been successful in spotting some of these transits, and so that's been a great effort. You can certainly reach out to astronomers working in exoplanet science at your nearby institutions to ask about opportunities or to ask for more information. And you can reach out to institutions like Lowell Observatory that will have educational programs that are sometimes focused on exoplanets. And if you're really passionate about this, you can always feel free to contact your local senator or representative to talk about funding for NASA and how, if you're excited about exoplanets or astrophysics in general, how you would like to support changes or increases in budgets to NASA to help drive the kinds of science that I was talking about here today. And so I would like to say that I am extremely fortunate to be able to work on these kinds of scientific questions. I do receive support from NASA, which is of course funded by taxpayers, which means I receive support from you all. And I am extremely grateful for that opportunity every single day.
Thank you very much, Ty. So we're going to wrap up the live stream now. This has been a ton of fun, and I just want to give Tyler a big thank you for doing this with us. Of course, we at Lowell, we miss everybody, and we can't wait until it's safe to educate you in person again. So with that, I'm just going to say thank you, and we're going to sign off.
Thanks, everyone. Thanks, Megan.